So in this lecture, we are going to explore a new kind of product between two vectors which yield a new vector. So this product is called the vector product or the cross product. So suppose we have two vectors, A and B. Then the cross product of these two vectors is denoted as A cross B. So this is the notation. So what does it mean? So to see what it means, let's take a two-dimensional plane. And let's take any two vectors that we want to find the cross product of. So this is a vector A and this is vector B. So given two vectors, we can always find a plane which is defined by these two vectors. And let the angle between these two vectors be theta. Then this plane defines two directions which are at 90 degrees to it. The first direction is given by what we are going to call the right-hand rule. So this is a direction n, which is 90 degrees with the plane that contains A and B. And we are going to denote this direction by right-hand rule. And the way we get this direction is if you take the four fingers of our right hand and curl the vector A towards the vector B, then the direction that our thumb points to is the direction of the unit normal. This is the essence of the right-hand rule. There's, of course, another direction we can get, which is also 90 degrees to this plane. And this is the opposite direction, and that is the direction that we're going to get if we use what is known as the left-hand rule. So for the cross product, the direction of the vector that results from the cross product of A and B is going to be given by the right-hand rule. That is going to be our definition. So more precisely, C will be given by the magnitude of the vector A, sine of theta, which is the angle, theta is the angle between A and B, times the magnitude of the vector B, times the direction, which n hat is a unit vector, given by the right-hand rule. So this is explicitly the definition of cross product. This is what it means. The right-hand side is what this symbol means. So let's look at a geometric interpretation of the cross product. So given two vectors, say A and B, so this is A and this is B, we can then define naturally a parallelogram in this way. Now, suppose that we drop the perpendicular from the tip of B to A. This is what we mean by B perp, and this is the angle theta between A and B. Then as you know, that the area of this parallelogram is given by B perp times the magnitude of A. But what is B perp? B perp is nothing but the magnitude of the vector B times sine of theta times A. For the sake of this discussion, we shall restrict the angle theta to be between 0 degrees and 180 degrees, which is in pi radians, it's pi. Later in the video, we shall see what will happen if the angle is greater than that. So what we see is that the magnitude of this vector is given by this quantity or this quantity. And this is the area of this parallelogram. And the direction is given by this. So here we see that in this expression, here we have, this is B perp. So this is of course symmetric, because if we take this parallelogram and suppose, so this is B, and again this is A, and now suppose that I drop a perpendicular from the tip of A to the vector B. So this is the angle. So I forgot to give the 90 degrees angle here. And then this is theta. Then this is a perp. This length is a perp. And then the area of this parallelogram, which is of course the same parallelogram as here, is still given, is given by this. And we see that over here in the expression for C, we also have, this is a perpendicular. So this is how we see, this is how we get the magnitude of the cross product. So to sum up, the magnitude of the cross product between A and B is given by the magnitude of A, the magnitude of B, times sine of theta, where we restrict the angle theta between 0 to pi, and the direction of C is given by, of course, the magnitude of C times n, which is the perpendicular. So let us calculate the cross product in the Cartesian coordinate system. So remember that in the Cartesian coordinate system, the three axes, the direction of the three axes are given by the unit vectors I, j, and k. So if I want to find out the cross product between A and B, and I want to call that C, I first want to express A in terms of I, j, and k. And then similarly B. So to find the cross product, we have to find out what is the cross product between the unit vectors. So if I take the two unit vectors I and j, so this is I and this is j, the angle between them is pi by 2. Then according to the right-hand rule, the cross product between I and j will be given by a vector which is pointing out of the page. We call this vector k. So we say I cross j is equal to k. Because we are using this to define our three-dimensional Cartesian coordinate system, such a coordinate system is called the right-handed coordinate system. Given a right-handed coordinate system, we can consider cyclic combinations of I, j, and k. So if I take I, j, and k, and I can consider cyclic combinations of I, j, and k and consider their cross products. So I can say I can take j cross k, and then that'll be given by I. And similarly, if I take k cross I. This will be given by j. Now, if I take what is known as the anticyclic combination, so if I just permute two of the vectors, and then any cyclic combination of this is going to give me the negative. So j cross I will give me minus of k, and then I cross k will give me minus of j, and then k cross j is going to give me minus of I. So in addition to these relationships, we also have I cross I will be 0, and that's because the perpendicular, there is no perpendicular, and the area of the parallelogram is 0. And then similarly, j cross j is 0, and k cross k is 0. So using these, we can now figure out what C is. So C is going to be AXI, AYJ, AZK cross BXI plus BYJ plus BZK. So, the cross term between this and this will be 0 because I cross I is 0. Similarly, the cross terms between this guy and this guy will be 0, and similarly these two guys. So what we'll have left is AX BY times I cross J plus AX BZ times I cross K, and then we'll have AY BX is J cross I, and then we'll have AY BZ is J cross K, and then AZ BX is K cross I, and then AZ times BY is K cross J. Now we can use these relationships and simplify this. So what is the first term? This is going to be AX BY times K hat. The second term will be AX BZ times minus of J. And then the third term will be AY BX times minus K. And then the fourth term is AY BZ times plus I. Fifth term is AZ BX times J. And the last term is AZBY times minus I. So we can now rearrange these according to their x, y, and z components. So the first term is, let's take this guy and this guy together. So we have AYBZ minus AZBY times I. And then the second term is going to be this guy and this guy. So we'll have AZBX minus AXBZ times J hat. And then the last term will be this guy and this guy. So we'll get AXBY minus AYBX times K. So this will be C. So what we have here is that this thing is C of X, this thing is C of Y, and this thing is C of Z. Also note that the relationship I cross J is equals to K, and J cross I is equals to minus K, and all those similar relationships mean that the cross product is an antisymmetric product. So A cross B is minus B cross A. And if you think about it a little bit, this also explains why we took the angle theta to be between 0 and pi, and what to do in case the angle is larger than pi. So this is how you calculate the cross product in a Cartesian coordinate system.